Hello, Chemistry 12. We are back with video 3 for week 5. We've been talking about the strength of acids and two ways of quantifying, I should say, the strength of acids is with a percent ionization calculation or with a Ka calculation. With a percent ionization, greater than 50%, essentially 99% quantitative reactions are your strong acids, less than 50% your weak acids, closer to, as the percentage decreases, the amount of ionization decreases with your acid. With Ka values, it's really a KEQ for acids, and so our benchmark is 1. If the Ka is greater than 1, you have a very strong acid. If Ka is less than 1, you have a weak acid. The lower it goes, below 1, the weaker the acid becomes. In this video, we're going to take a look at bases, take a look at strong and weak bases, and instead of calling it the ionization constant for acids, it's the dissociation constant for bases. And so Ka will become Kb. With strong bases, they're quite easy to recognize. It's the ionic hydroxides. So any compound, or I should say any ionic compound that has an anion of OH hydroxide is representing a base. And for the most part, they represent strong bases. There's a few exceptions we'll talk about. But generally speaking, a compound that has OH as its anion is going to be a strong base. They do vary in solubility, and so that's where there's a few exceptions, and we'll talk about that in a minute. When we take a look at a strong base, we look for that hydroxide. And when we look for that hydroxide, we right away, boom, that's how we've been identifying bases for a long time now. And so what we see, just like before, dissociation or ionization, it's the splitting apart. And so sodium hydroxide will break into Na positives and OH negatives, and barium hydroxide, Ba2 positive and OH negative. Take note of the charges and the AQ for each of our ions. It's important to write that down, charges and AQ. I've circled the coefficients here because we need to be clear on that. Here we have sodium hydroxide, so it's kind of like a red Lego and a blue Lego, and when we separate, we get piles of red and piles of blue. So if we had 100 sodium hydroxides, red, blue connected together, if we dissociate those pieces, we would get 100 of sodium ions and 100 of hydroxide ions. The same thing here, we have one barium, but because of its ionic charge, we have 2 hydroxides to balance that out. So we have twice as many hydroxides here. So that subscript's important. So it's like having a blue piece with 2 reds attached. One unit is 1 blue and 2 red. When we break that unit apart, we have blue, but we have twice as many red. Okay, so the coefficient's going to play a part. And the first thing we want to recognize is here, right from the beginning, talking about acids and bases, we know that OH, right, is really important for a basic solution. And basic solutions, it's all about how many OHs they have. As the OHs go up, the H positives go down so that they can keep their balance. So here you can see barium hydroxide is actually going to release twice as many OHs into the solution as opposed to sodium hydroxide. Sodium hydroxide here, it's a 1-to-1 ratio. So they'll, produce an equal amount of OHs as NaOH, as NAs. Here with barium hydroxide, though, we have that subscript 2, so we have a 1-to-2 ratio. So here you're going to have twice as many OHs as you do barium hydroxide. When this happens, because barium hydroxide is soluble, you're going to get a higher concentration of OH negatives there, and therefore a stronger base. The pH and conductivity of barium hydroxide solutions are found to be higher than those of sodium hydroxide, and that's what you're going to find out. Barium hydroxide, it's going to give you a pH level is going to be higher than sodium hydroxide. Remember, a high pH means very basic. So barium hydroxide will have a higher pH measurement. Also, we talked about electrolytes. And Electrolytes are solutions that conduct electricity very well because they have many charged particles. Barium hydroxide would have a higher conductivity than sodium hydroxide because it's releasing twice as many OH charged particles into the solution as sodium hydroxide. I do want to point out here, just for your chemistry knowledge, the solubility chart is important when you're talking about strong bases, because if you look on the solubility chart on the back of your periodic table, and for instance, we'll take a look at calcium hydroxide and barium hydroxide, both of them, because calcium and barium are in the same family, group 2, you'll have a subscript of 2 here for your hydroxide. So most people would assume that these guys would have equal conductivity and equal similar pH levels, and that is actually incorrect, because if you look at your solubility chart, barium hydroxide is quite soluble, but calcium hydroxide has low solubility. So even though we recognize it as a strong base because of the OH, in fact it actually has very low conductivity, and that's because it is not soluble in water, so it doesn't dissociate as well as we would think it would. When you look at group 2, you'll notice as you move down group 2, the solubility increases. So barium and strontium hydroxide have high solubility, calcium hydroxide does not. Okay, so just for a little piece of information there. If you're wondering how strong a base that has OH is, you check the solubility chart and that'll give you a hint. So strong bases, look for that OH, and they're 100% ionization for the most part. If they have low solubility, then their percent ionization or percent dissociation will drop. The other thing I want to mention before we go too far is the difference between a strong and weak acid or base versus a concentrated or dilute acid or base. A lot of people mix these up, or they think they mean the same thing, and I want to be clear that they do not. The word strong and weak, hopefully we're okay with that now. That's all about how well they dissociate or how well they break apart. So the words strong and weak are referring to the extent of ionization or dissociation of an acid or a base. Okay, so if they break up very well and they have 100% ionization, we say they're strong bases, they're strong acids. If they have low ionization, for example, acetic acid 1.3, that's a weak. So strong and weak, you're really only referring to how well they ionize in water. Concentrated and dilute is different. Concentrated and dilute, it's all about how many moles are packed into 1 liter of water. So it's a measure of the moles of moles of acid or base in 1 liter of water, as opposed to how well they're ionizing. So, for example, sodium hydroxide, it's a strong base, right? So it ionizes really, really, really well. So it's a very strong base. But if you look at the different concentrations, 0.1 molars, so you'd have 0.1 moles for every liter, versus 0.001 molars, you'd only have 0.001 moles per liter. So even though it's a strong acid, it can be a strong base, it can be dilute in some situations, and it can be concentrated in others. If you want to pause right now, we have a few textbook questions that are really, really good practice. I'm going to go on and actually look at a couple answers right now, and one of these slides will be the answers for all of them. But if you want to pause and try these questions first, just to see how you're making out, and you can come back again and we'll talk about the answers. So you might have just paused. You looked at questions 24 to 29 on page 611. If you didn't pause, I know, I can tell. You should pause now and go back. I wanted to point out 2 of the questions because I think it's really covering some important information, and I will flash the answers for the rest of them. They are in your textbook, the answers, and I will post this PDF and you can check the slide. I think it'll be slide number 18 in this PDF will be the answers to these questions. So the first question, 24, it says compare a strong acid and a weak acid in terms of acid dissociation. So here we're thinking about strong and weak again. So it's acid, you want to talk about how well they're breaking up. This is such an important concept, and I want to make sure you guys are okay with it. Dissociation, ionizing, dissociating, it all means the same thing, right? It's all about a compound breaking up into its ions, acids breaking up into their ions, bases breaking up into their ions. So we want to be clear on this. So here's a picture that might help out. Okay, we have HCl here, and what you can see is that the dissociation has happened already. So we have our big C's, the purples, and we have our H's, the little reds, but they're not together. They've separated. So the Cl negatives and the H positives, they're all in their ion form. Over here you can see some have separated, but some are still together. And so this would be a strong acid, 100% ionization, dissociation. This is a weak acid. So these guys, they haven't broken apart. They're staying together. This is acetic acid. But here we have an acetate ion, we have a hydrogen ion. So we've got some breakups, but not a full breakup. And so this would be a weak acid. If you look at Kas, what are Kas going to tell you? So when you have a low Ka, that's all about a weak acid, okay? And if you have a high Ka, it's about a strong acid. So 1 is our benchmark, greater than 1, less than 1, okay? The other question I wanted to highlight, so you'd go back and take a look at it, is question 28. Like I said earlier, there's a couple ways you can draw, or you can write out dissociation equations, and that's going to be our focus for next week, really. So I wanted you guys to get a head start to look at these dissociation or ionization equations. And so I'm going to do the first one with you here, and it's for nitric acid. So if you take nitric acid, and again, you've got your acid-base table, so if you don't know what the chemical formula is for it. So I've got nitric acid here. That H is red on purpose because that's the H that's going to be given away by nitric acid. It only has 1 to give away. And we're going to add it. So we are going to start getting into the practice of including water in. I know we haven't done it up until this point, and that's okay. But we're going to start getting into the habit of including water in our reaction. It is an equilibrium, okay? And so what's going to happen here? Now, I like to write my water HOH, and that's probably because I'm a biologist pretending to be a chemist, pretending to be a physicist. But HOH, it shows me that I have an H positive and an OH negative coming together to make that water. You can use H2O as well. It's up to you. But what happens here is because this is acidic, right? What's going to happen is this guy is going to come over, right? This guy, that's where the H3O comes from. So H2O, H3O. But remember the positive sign. So these ions we are picky with. So we have H3O positive. It used to be H2O neutral. Now it's H3O positive. We gained an H, so we gain a positive charge. Aqueous, it's an ion, so it has to be aqueous. What's left over is not this guy. What's left over is our NO3, but we don't want to put it as a superscript. NO3 negative. Okay, so that's what's left over from our nitric acid. So that's what we're going to work on for the remainder of this week and onto next week, is getting comfortable writing out these dissociation equations. Okay, and that's the first one done there. So think about it and take some time, stop right now if you need to finish up those 3, and the answer's on the next slide. Okay, so equilibrium, this H being taken from this water to make this guy and this ion here. Look at the charge. He was, get carried away with my charges. He was neutral over here, nitric acid, neutral over here, but when the H went, when he lost his proton, he became negative. So think about those charges when you're putting these things together, okay? Here's the rest of the answers. So this is slide 18. So if you take a look at the PDF later, slide 18 is the answers. Also in the textbook. Moving right along, I want to talk a little bit about weak bases, and I wanted to do a few problems with you, just so you're ready for the assignment. So weak bases are kind of an interesting thing. Weak acids and strong acids, both of them have H's or COOH's, so they're easy to recognize, and we can see where that H is coming from. Weak bases are not always as visible. strong bases, easy to pick out. You're looking for that hydroxide. So if it has OH, it's good. For the most part, anything with OH is going to be a strong base. There's a couple exceptions because of solubility. But weak bases, how are weak bases going to create OHs? Because remember, that's what a base is. A base is when the OH concentration is a lot higher than the H plus concentration. So these are substances which dissolve in water to produce basic solutions, but do not contain a hydroxide ion. So they're sneaky. Sometimes we don't recognize them. And a very common one is ammonia, right down here. Weak bases react non-quantitatively. What that means is it's going to be an equilibrium, okay? So it's not a quantitative reaction. So weak bases are involved in an equilibrium equation with water to form equilibrium that includes aqueous hydroxide ions. So they might not have hydroxide in their formula, but they produce hydroxides when they mix with water. So essentially you take your weak base, you add it to water, it's an equilibrium. And so what's happening to water here? And remember, I like to use this guy, right? So where's the OH come from? It's not coming from the base. The base is indirectly creating that OH. The OH comes from water. So if you remember just the last question we looked at, we had this HOH and it took this hydrogen and it became H3O positive. Now when we're looking at weak bases, we have this HOH and it's going to give away a hydrogen. That's where that OH comes from. It's when water gives away a hydrogen. Okay, so the base here is not going to give anything to water. A weak base actually takes something from water. It takes the H away from water, and therefore you're left with that OH. And we don't care how we got it, because now we can have a basic solution because there's more OH there than anything else. Okay? So example, ammonia, not ammonium. Ammonium is NH4 positive. Ammonia, NH3. We're going to mix it with some water. If you want to think about HOH, if that helps. And we want that OH, so we take the H away. Look, this guy used to have 3, now he has 4 H's. Okay, this is a dissociation equation for a weak base, right? Water gives that H to the weak base. We have this guy left over, which is going to create our basic solution, and we've got this. Now be careful. He was neutral here. He was happy, in with 3 H's. Everybody was balanced. It was good to go. He took an extra H, though. H's are protons, they're positive. So now he's NH4, but he has a charge. So we're picky with AQs and we're picky with charges when we do these dissociation equations. Okay? So a weak base. This guy, looking at him, why would he be a base? Who knows why he's a base? Well, it's because he can take an H away from water and create that OH negative ion. This formula hopefully looks familiar. It's for Kb now instead of Ka. So we only have to change up a couple things. With Ka, it's all about the H plus, because we're talking about acids. With Kb, it's all about the OH negative, because we're talking about bases. So we will need to know that OH concentration, and we're going to square it. Why? Because it's always a 1-to-1. So with these ions up here, it's always a 1-to-1 ratio. So if you know how much this is going to be exactly the same thing. So just to save time, OH negative squared. Here we used to have an HA for acids. Now we have a WB for weak bases. Okay, so weak bases or base, Kb. Same process. It's the KEQ for a basic dissociation as opposed to an acid ionization. Okay? All right, let's try a couple examples here. I'm already at 18 minutes. Let's take a quick look at this. So, the pH of a 0.1 mole per liter sodium carbonate solution is measured to be 11.66. What is the Kb for the carbonate ion? So we're going to talk about something called a spectator atom in this question here. But because we want to focus on our dissociation equations, let's think about what's the equation going to look like here, right? Sodium carbonate, we want to know the Kb for the carbonate ion. Now, most people want to start out with sodium carbonate, but in fact, right, this is our equation here. Write out the dissociation in water. In other words, Na2CO3 in water. What are the entities? So here's my sodium carbonate, but the sodium carbonate is actually not the weak base here. How do I know I'm talking about a base, first of all, before I go any further? Big hint here, Kb. Use your hints to help you out. So Kb, we know we're talking about a base. So sodium carbonate is a base. But in fact, it's actually the carbonate ion that's the base. The sodium is known as a spectator ion. And so it's highly soluble. Anything in group 1 is highly soluble. So when we put sodium carbonate into water, they split right away into sodium ions and carbonate ions. It's actually the carbonate ion that's going to work as a weak base. Okay, you can put the sodium there. It just kind of messes things up because it doesn't balance out very well. You can put the sodium here. It's just going to be a plus sodium ion over here. It's called a spectator ion because it's in the beaker, but it's not taking part in the reaction. So sodium carbonate, it's that negative anion that's going to be the weak base. So here's the weak base. Take note, sodium, there's 2 sodiums linking up with it. Sodium's plus 1. So when it's on its own, it's an ion. It has a charge. So carbonate, 2 negative, okay, aqueous. Water, you can think of HOH if you want. HOH, we've got to get rid of an H. That H heads over here. So the H heads over here. So you have your hydroxide and you have your HCO3. Look at the charge. It was -2. It got an extra proton, it got an extra H, and now it's -1. Okay, so take note of charges. Okay, we want to find Kb. What do we need to know? Well, if we get into the habit of underlining what we know up here, we know we have a pH, all right? We know we have a concentration. Sodium carbonate, it's also the concentration of carbonate ion, right? So we've got a concentration there of our base, and we're looking for Kb. So we have an equation for Kb. It's OH squared over weak base. So carbonate is our weak base. We have our concentration for our weak base. We need to find OH. How can pH help me find OH? Thank goodness we did the equilibrium unit before now. So our pH can find our OH 2 different ways. You could take 14 minus 11.6 and get your POH and then change it to OH. Okay, or you can find your or your H positive and then use KW to find your OH. So there's a couple of different ways you can do that. Okay, I would probably go this way. It's just a lot faster. So we know these 2 add to 14. If we subtract them, now we have the POH. Then we can use that to find our OH concentration. So don't forget too much about that pH, POH from unit 2, equilibrium. Okay, so we plug it into our calculator, and we've found our OH concentration. We've got it, our OH concentration. All right. And so, Kb, OH squared over CH3, 2 negative. Take our concentration, which we found thanks to the pH, square it, put it over our concentration of our substance, and we get a Kb of 2.1 times 10 to the negative 4 moles per liter. Okay, so Kb is working the same as Ka, essentially the same formula, but it's OH we're working with now, squared over our concentration. A lot of you guys are probably saying, gee, I wonder if ice tables happen here. And yes, they do. We didn't use an ice table here because we didn't have our Kb, but we did have our OH concentration. So we could have used an ice table. I think we probably were okay without using one, but it wouldn't be wrong to use an ice table as well, maybe a little more work. So I'm going to do 3 practice problems with you, and then we'll call it quits, meaning quits for the video, and you guys can get on to the assignment. So our first question here, and I'll just close it up so that we don't see too much at once. Hopefully it looks familiar because I think it's actually the first question I put on your assignment for you when it comes to calculations. So your first question here, it says, determine the molar concentration of all substances in a 1.000 decimeter cube volumetric flask filled with a water solution containing 1.750 moles of boric acid. Okay, so this is boric acid, H3BO3, boric acid. Our Ka is 5.8 times 10 to the negative 10. And note, it's been a while since we talked about decimeters cubed. 1 decimeters cubed equals 1 liter. So this is the same as saying 1 liter. Okay, so we're working in a 1 liter volumetric flask. So we're looking for the concentrations of everything, okay, of all the substances when we put boric acid in water. So step 1, let's work on our dissociation equation, right? What's going to happen with boric acid? How is that going to break apart? How's that going to dissociate or ionize? Okay, think about it. So H3BO3, here's our water, again, or HOH. This is an acid, right? So how do I know that? Ka. So it's an acid because it's Ka. And so I know that this guy is going to get rid, I want to make it H3O, right? Kas, you want to make H3Os. Kb, you want to make OHs. So this guy, H2O, he needs to get an extra H. He's going to get it from the boric acid. And if you recall from the last video, acids lose their H's one at a time. So we're just looking at this movement of this first H. So one H comes over here to the water, H3O positive, and H2BO3, look at the charge. Here it's neutral, here it's -1. It lost an H, it's -1. Water is neutral, it gained an H, +1. So H's bump up the positives. My next question, I guess it's right here in green, do we need to use an ice table or not? And remember the approximation rule. If your Ka is greater than 10 to the 4 or smaller than 10 to the -4, the change in ions is too small to worry about. So our Ka is 5.8 times 10 to the -10. So we can use our approximation here, right? We don't have to worry about an ice table. No ice table necessary. If your Ka or Keq or Kb, whatever you're talking about, if it's smaller than 10 to the -4 or larger than 10 to the 4, that's the approximation rule. You don't have to use an ice table because the amount of ion being produced is too small to worry about. All right, so if we're going to underline what we're looking for here, we know our volume, 1 liter. We know our moles of our starting acid, right? So that's also molarity. So we know the molarity of our acid. We know our Ka, perfect. And we're looking for our concentrations of all of these things, right? So they gave us this. We're really looking for our concentrations of our ions here. Remember, this is liquid, so he's not going to be involved at the Ka. This one you probably did in your head, but just to be clear, concentration is moles over volume. So we take our moles, put it over volume, and we get our molarity for our starting solution. Here's our Ka, H plus squared, H3BO3. We know our Ka, we know our H3BO3. We're not going to put minus X because our Ka is less than 10 to the -4. So we can kind of ignore that minus X. And we have our H. We can cross multiply and solve for our H plus. Okay, so our H plus works out to be 3.186 times 10 to the -5 molars. That would also be for your H2BO3 negative ion. Both would be the same. Okay, 4 sig figs. And the reason why 4 sig figs here is because I had 4 sig figs here and I had 4 sig figs here. I only have 2 here, but because this is a constant, we don't count our constants for sig figs. All right, so it's 4 sig figs because of the values that we had in the question. All right, just going to squeeze 2 more examples in. I know I'm getting late again. I'm almost at 30 minutes, so I'll quickly do 2 more just to help you out before you start the assignment. Calculate the hydronium ion concentration. Calculate the hydronium ion concentration in a 0.045 molar HIO aqueous solution if the Ka is 2.30 times 10 to the -11. So these are the types of questions you're going to find on your assignment. So hydronium ion, we're looking for H plus. We know the concentration of our starting. We know it's a solution. We know it's an acid, Ka. Also, it starts with an H. Okay, so we know we're talking about an acid. Is it a strong acid or a weak acid? And if you're shouting strong, you're wrong. If you're shouting weak, you're right. Because look, Ka is really, really tiny. That's an indication of a weak acid. All right, so we have our concentration of our acid, Ha. Will we need to use an ice table? Right? Do we have to use this minus X? And the answer is no. Right? Less, if your Ka is 10 to the negative 4 or less, then it's the amount of ion being produced is so small, we don't have to worry about it. If you take a look at your equation, this is what we're supposed to be practicing with, right? HIO, we're including the water now, HOH. We know we're working with an acid, so we want to make H3O positive. So this is going to gain an H, and this is going to lose it. Take note of the charges. This is neutral. It gets an extra H. It becomes positive. This is neutral. It lost an H. It becomes negative. So every H you lose, you decrease in charge. Every H you gain, you increase in charge in the positive way. Do we need an ice table? The answer is no. So instead of putting minus X here, because we have such a small Ka, we don't have to put minus X. Okay, so plug your numbers in. We get to leave this guy out because, oh, come on. Arg. I don't know what the problem is. There we go. Right, we can leave him out because of our approximation rule. Plug it in, get our X. I just want to mention one thing here. X is not your concentration. It's the value you found. You should let me know what X is representing. So just circling this as your answer is incorrect. You should increase or go one more step and say X is referring or representing H plus, which is equal to IO negative, which equals this, and put in your unit. Okay, so don't just give me an X equals. So let me know what X is representing and put your unit in if it's necessary. Kas do not need units, but concentrations do. And our last one here, this one, I wanted to do one that actually needed an ice table. So we'll take a quick look here. If the first ionization constant for phosphoric acid is 7.1 times 10 to the negative 3, what will be the pH of a 0.10 molar solution when equilibrium is reached 25 degrees Celsius? So, reminder, first ionization constant, phosphoric acid, H3PO4. It has 3 H's to give away, but it gives each of those H's away one at a time. So we're just going to look at the equation where the first H leaves. Okay, it has a ionization constant. That's Ka. That's what Ka is, ionization constant. So the Ka is, ooh, guys, 7.1 times 10 to the negative 3. We cannot use our approximation rule. It's not greater than negative 4 or larger than positive 4. So we're going to use, that's how you can tell, we're going to use an ice table here, okay? Our initial for our solution is 0.1, and we're wondering what's happening at equilibrium. We want to find the pH. How would we find the pH? The pH is going to be, right, we can't find that directly. So we're going to have to find something first and then find the pH. And you're right, we're going to find the H positive first and then the pH. So what's our equation going to look like? If you're thinking about dissociation, this is what we want to start practicing. It'll be more important next week. So if we take it and check your acid-base table, if you forget what phosphoric acid is, look it up on your acid-base table. So H3PO4, we're going to add it to some water. It's an equilibrium. We are working with an acid, right? So we're trying to make H3O positive. So this guy has to gain an H. So this guy's going to lose an H. He's neutral now. When he loses an H, he has a -2 charge. Okay? Because he has 2 H's left, right? He was neutral here, and so he's negative. Sorry, he's not negative. He's -1, not -2. Oh, golly, you know what I mean. Finicky, finicky, finicky. There we go. A -1 charge. This guy here, he's neutral. He gains an H. He becomes positive. Okay? Do we need an ice table? And we mentioned that already. Yes, we do. This guy is not greater than -4, not less than -4, and not greater than +4, our approximation rule. So here's our ice table, lovely ice table here. And what we've got is our initial. We had lots of acid. We don't have any of our ions yet. That should be -1 there. I'll fix it in a minute. I can't, it's bothering me. But same dealio. I wish my computer had memory. Okay, there we go. So we have our ions, we're starting with 0. We have our acid, which we're starting with. We know we have a change. It's a 1-to-1 ratio. Always will be, because they're losing 1 H at a time. So this guy is going to subtract X. Here, we're going to add X. All right, 1-to-1-to-1. So here, we're going to just have X, 0 plus X is X. Here, 0 plus X is X. And here, we've got to find out what that X is, right? We're not quite sure what that X is going to be. So what we do is we take our Ka expression, right? And then when we plug it in, can we get rid of this -X? And that's the thing. We cannot cross it out this time. Our approximation rule doesn't work. We're going to make enough ions that they will affect the overall amount at equilibrium for our acid. So we're going to leave that in. And when that occurs, we need to, so I don't have to reveal that yet, but when that occurs and we start calculating, this is what we find. So we get that quadratic equation when we have to leave the -X in. Okay? So here we cross-multiplied. Here I multiplied each thing. And then I've got this. So my A value is 1. My B value is positive 7.1 times 10 to the -3. My C value is negative 7.1 times 10 to the -4. Plug that into your calculator or, on the web, and you can use your equation, and you come up with an X value of 3.1 times 10 to the -2. No units, it's an X value, right? So what is X representing? So when we come back up here, now we have a value for X, 3.1 times 10 to the -2. So this is going to represent by X. It can also be represented by 3.1 times 10 to the -2, 3.1 times 10 to the -2, 0.1 minus X, 0.1 minus 3.1 times 10 to the -2, and now we have a new value. See, it's quite a drop. It's big. We made a lot more ion than we did before. So the more ions we make, the more often we have to put that -X to represent the ions that we made. Okay? Now that we have these, it's very quick to come up with your Ka. Sorry, we have our Ka. It's very quick to come up with your pH. We have the values here for our H3O positive, for our H plus. And so we plug that into our formula, and we get a pH of 1.51. Okay? So you might say, wow, that's a strong pH. This must be a strong base. Not necessarily. Remember the difference. Strong and weak acids and bases, it's all about how well they ionize. Concentration, which plays a part in pH. You can have a weak acid, but a very concentrated weak acid. You can have a strong acid, but a very dilute strong acid. So the pH is wrapped up more in the concentration and dilution versus the strong and weak. Okay, so that finishes off our last video for week 5. Just wanted to quickly end with the relationship between Ka and Kb. Here, if you multiply your Ka and your Kb, it works with Kw. So it's very similar to that teeter-totter we saw with H plus and OH negative. These are multiplied together to get Kw. Or you can rearrange it if you want. So if you know your Kb and you're looking for your Ka, you can use Kw in that case. We don't use this formula very often at all. The formulas you want to remember are your Ka, your Kb, and your percent ionization, and also your pH and pOH formulas. That's what's going to help you out in this unit. Thanks for your attention. Talk soon.